Assalamualaikum and hi, we are from Group 4 and welcome to our video presentation. Before begin, this is basically our group member. So this is the standard second order differential equation for a damped spring mass system. We simplify using damping ratio and natural frequency omega. Based on Newton's second law, we derive the equation of motion by summing the spring and damping forces and dividing through by mass to simplify it. By substituting damping ratio and omega, we solve the characteristic equation and classify the four types of damping with their respective general solution.
For undamped, we will find natural frequency first and we get 2.014. Next, using the general solution equation for undamped, we let t equal to 0 and we get a equal to 1. Next, we will differentiate xt and let t equal to 0 into x prime t. So we get 2.014b and we get b equal to 0. Finally, we get the equation for undamped xt equal to cos 2.014t. For underdamped, we have to find damping ratio and damping frequency. So we get y equal to 0.707 and omega d equal to 1.886. Using the general solution, we let t equal to 0. Then we get a equal to 1. Then we differentiate xt. Then we let t equal to 0 into x prime t. And we let it as equation number 2. We substitute a equal to 1 into equation 2. And we get b equal to 0.375. Finally, we get the equation for underdamped. So here is the graph for displacement versus time for undamped and underdamped. Basically, this graph we obtained from the equation that we calculated previously.
For the critically damped condition, we need to ensure that our damping coefficient y is equal to our natural frequency omega. However, using the initial m, k and c values from the problem, our system would be underdamped. Therefore, to demonstrate the critically damped behavior, we must just adjust the damping coefficient c while keeping m and k constant. After all the calculations we done, we have the displacement equation for the critically damped condition. It is x of t equals 1 plus 2.014t O times e to the power of negative 2.014t. Similar to the critical damped case, to achieve the overdamped condition, we must again modify the damping coefficient c. For overdamped behavior, our y values must be greater than omega. Therefore, the displacement equation for the overdamped condition is x of t equals 1.045 times e to the power of negative 0.420t minus 0.045 times e to the power of negative 9.656t. And here we have the graph displacement versus time for critically damped and overdamped.
Now we will discuss the results obtained. First, for the undamped case, the system oscillates continuously without losing energy. However, this is not realistic in real-world system where friction and resistance are always present. In the underdamped condition, the amplitude gradually decreases. This reflects most real suspension systems where the oscillations reduce over time but do not disappear instantly. For the critically damped case, the system returns to its equilibrium position as quickly as possible without oscillation. This is ideal in suspension system for fast stabilization. In the overdamped condition, there is no oscillation either, but the return to equilibrium is slower, which may reduce responsiveness. In conclusion, each damping type affects how the coilover system behaves. Underdamped and critically damped systems are generally the most practical, offering a good balance between comfort and control. This concludes our presentation. Thank you for watching, and we hope this explanation helps in understanding damping behavior in real-world applications.
Thank you.